Welcome, pre-calculus honor students, to 8-1 simple trig equations, and we're going to try and solve simple trig equations and apply them. Simple implies that you have an equation that can turn into one trig function set equal to a numeric value. Like, when does a sine equal a half? Well, there's two approaches. There's the graphing solution, that is, look at y equals sine x and look at y equals a half and see where they cross. And we see two crossings in here. Now, at this point, you might not recognize what those exact rating values are, and I'll expect you to know that. That's why I also recommend this unit circle approach. Let's take a look at this. In the unit circle approach, we look at sine of x equals half, and we say, when do the y coordinates equal a half on the unit circle? So we mark a little half right here. We scoot over this way and this way. And we get an angle here and an angle here. And by now you should know your simple trig values, your special trig values, and this happens at pi over 6 and at 5 pi over 6. So there's your answer to this simple trig equation, x equals pi over 6, comma 5 pi over 6, two possible angles. Now, actually, if you think about it, these are particular solutions asked for between 0 and 2 pi. And that's usually what I'm going to say, from 0 to 2 pi. But technically, if I just said solve sine of x equals a half, the answer would be x equals pi over 6 plus 2 pi k, or x equals 5 pi over 6 plus 2 pi k. And these are infinite solution sets where k equals any integer. So you keep on coming up with all the angles coterminal with pi over 6 and also coterminal with 5 pi over 6 for an infinite solution set. Now, in general, though, I'll be asking you for this limited solution set from 0 to 2 pi once around the unit circle. But we'll come back to this idea when we start solving more complicated equations, that sometimes you get more than just two answers. Okay, find the values of x between 0 and 2 pi for which the sine of x equals 0.6. So we can use our calculator to say x equals the inverse sine of 0.6, and we get this one answer. But we know there's more answers. And if I set up a unit circle, it doesn't have to be real precise. 0.6 is up here, and see how the calculator has given me this rating answer of 0.6435. But there's another answer, let's call this x1. There's another answer, x2, which will have the same height as this one, but it'll be in the second quadrant. Well, we can think of what the calculator gave us as the working angle here, and so that same working angle is going to be used to, or reference angle, is going to be used to create the angle in the second quadrant. So we're going to have to back up from pi. So our x2 answer is going to be pi minus the 0.6435. And that's where we get our other answer from, 0.2498. So notice two answers between 0 and 2 pi for that one. Now, to the nearest 10th of the degree, solve 3 cosine theta plus 9 equals 7 for 0 is less than or equal to theta is less than or equal to 360. So first we solve this for cosine to form the simple trig equation. And this is what we were talking about at the very beginning. A simple trig equation is one trig function equal to one real number. Cosine theta equals negative 2/3. And now we have to understand, well, where are we going to get our answers from? Well, we can get one answer from the calculator just by doing inverse cosine of negative 2/3, and it tells you 131.8 degrees. It actually gives you a second quadrant angle. Now, to get the other answer, that gets a little trickier, though. We have to look at where this first answer was. And it was a second quadrant angle way over here. So here's theta 1 at 131.8 degrees. To get this second answer now, we're going to have the same x coordinate as this one on the unit circle. So that means we're going to have to be down here. So it's going to be the mirror image over the x-axis. It's going to be clockwise rotation instead of counterclockwise rotation. So theta 2 will just equal negative 131.8 degrees. The thing is, we were asked to give the answers from 0 to 360, so we add 360 on to get the angle coterminal with that. So you end up with two answers. Two answers. 131.8 degrees and 228.2 degrees. That'll work for that simple trig equation. Now, some other people feel more comfortable using the reference angle approach, and let me just show that real quick. The reference angle approach is when you figure out the reference angle, alpha, by taking the inverse cosine of 2/3. And that ends up being inverse cosine 2/3, 20 is 48.2 degrees. And then you use this 48.2 degrees and go that far into each of the appropriate quadrants. We know that cosine is negative. Cosine theta is less than 0 in quadrants 2 and 3. So we take that reference angle wedge and we go that far into each of those two quadrants. So from 180, we're going to subtract the 48.2 and add the 48.2. So 180 plus 48.2 and 180 minus 48.2. And you'll get the same answers I got before. Now, in either way you think about it, the point is to draw a picture. A lot of students will sit there and say, well, why'd you add 180? Why'd you subtract it from 180? How'd you get this formula? This is not so much a formula as a visual thinking of where you are in the quadrants and what the working angle is going to be in the reference angles. So inclination and slope. The inclination of a line, alpha, where 0 is the angle alpha between the x-axis. So we can draw a line. There's the x-axis and the y-axis. And then we have some line that goes like this. And the working angle alpha then is this wedge like this. Here's alpha. So the inclination of the line is the angle alpha between the line itself and the and the x-axis. So let's look at another diagram of this is what we mean by working angle. What we mean by inclination of a line. Let's put another x-axis down, or a y-axis and an x-axis. And let's say our line is like this. Where's the angle of inclination? Well, let's look carefully at the diagram. We go from the x-axis and rotate, and we want to keep it between 0 and 180. So there you go. There's your inclination angle. Okay, so here's a useful theorem. For any line with slope m and inclination alpha, slope m equals the tangent of alpha, as long as alpha isn't equal to 90. If it is 90, then it has no slope. Now, find the inclination of this line, 2x plus y equals 15. Well, as you recall, we have a couple ways to come up with the slope. This is in standard form, so we can go negative a over b. So that's a negative 2 over 5. You could also rearrange it into y equals mx plus b form. In either case, we get the slope is negative 2/5. And so the tangent of the angle of the slope equals the tangent of the angle of inclination. So negative 2/5 equals the tangent of alpha. And alpha is the inverse tangent of negative 2/5, which is about negative 21.8 degrees. Now, we just have this general guideline that alpha is between 0 and 180, so we add 180 on it to get that for our angle of inclination, 158.2 degrees. Now let's go on to 8.2, sine and cosine curves. To find equations of different sine and cosine curves and apply these equations. Let's recall the effects we studied back in 4.4. That is, if we start from our basic sine functions, and first of all, usually we would graph this from 0 to 2 pi, so let's review the key points on the sine wave. Halfway through is pi, that's we hit 0 again, and you get a peak at pi over 2, and a nadir at 3 pi over 2. So there's your peak. And we talked about omamo, that you graph the 0, the max, the 0, the min, and the 0 again for the sine wave. and has an amplitude of 1. Amplitude is max minus min divided by 2, so the amplitude is 1. And the period is 2 pi. The cosine goes mama, starts with a max, ends with a max at 2 pi. Halfway through, you're at a minimum. Quarter of the way through at pi over 2, you're at a 0, and also at 3 pi over 2, you're at a 0. Now what change is happening in the blue function here now as we start deviating from our normal y equals sine x and y equals cosine x? Well, in this case we see the coefficient in front, and that has basically then changed the amplitude. So changed to 2. Now in this one, again we see a change in amplitude, but there's also two things going on. With a negative a half, that negative creates a flip over the x-axis. And again we have an amplitude change. The amplitude is changed to 1/2. Remember, the amplitude is the absolute value of this coefficient on the cosine. So we get 1/2. Now we start messing with things inside the sine wave. Y equals sine 2x. So this is a period change. We normally had a period of 2 pi. Now the period is just pi. Pi over 2, pi over 4. These become our key points that we're going to want to graph. 3 pi over 4. So the period now is 2 pi divided by the coefficient on x. So 2 pi divided by 2, and we just have a period of pi now. Now with this graph, something strange happened. Y equals x over 3. So now the period is again 2 pi divided by the coefficient on x, which is a third. So we end up with a period of 6 pi, which is over 18, for our blue cosine x over 3. Okay, and here's some of our conclusions from doing period and amplitude sketches. That is, for functions y equals a sine bx and y equals a cosine bx, we can come up with the amplitude as the absolute value of a, and the period is 2 pi over b. Now the text does this thing with a cannot equal 0, and I can see that because you don't have a function. You got y equals 0, you got a function, you just got the x-axis. But they restrict it to be greater than 0. I'd like to put it to you that we don't have to restrict b to being greater than 0. We can just restrict b to being not equal to 0 like a, because otherwise you'll just get y equals a. So that means we do have to tack this on to our formula for the period, 2 pi divided by the absolute value of b. Okay? Okay, give the amplitude and period of this function, y equals negative 4 sine 3x, and sketch at least one cycle of its graph. So the amplitude is just the absolute value of that coefficient in front of the trig function. So the amplitude is 4, and the period is 2 pi divided by the coefficient on x. So that's 2 pi over 3. So for graphing this now, let me give you some tips. First, the vertical the y-axis. Put your tick marks, you don't have to have a tick mark for every one. You can just put your tick marks equally spaced here to represent the max and min function, and that will represent our amplitude. So we get an amplitude of 4. So we'll have a peak of 4 and a bottom of negative 4. Now, for the x-axis, mark your first tick mark anywhere. Now put the second tick mark halfway in between those two. Halfway between the y-axis and your first tick mark. And then cut those each in half again. And you'll get a decent scaling for your trig wave. Now, labeling the axes. Labeling the axes, we start with the period. And we're essentially going from 0 to 2 pi over 3. Cut that in half. Half of 2 pi over 3 is 1/2 times 2 pi over 3, or pi over 3. And then cut that in half again. Half of pi over 3 is 1/2 times pi over 3 is pi over 6. And so this will be halfway between these two. You can do the average, or you can just triple this. 3 times pi over 6 is 3 pi over 6, which is pi over 2. 3 times pi over 6 is 3 pi over 6. And that's where I got the pi over 2 for up there. Now the actual graphing. Sine goes omemo, but we have a little change here because the sine goes omemo, but because it's the opposite of 4 times all this, we're going to go omomo. It gets flipped over the x-axis. So we go 0 minimum, 0 maximum, 0. And then sketch on through. There you go. There's your sine wave. The trick here is to basically scale up your x-axis with the convenient tick marks of what your period is. Notice when I did this on GeoGebra, it gave me the whole thing from 0 to 2 pi. And here you go. 2 pi over 3 is about 2. Now, give the amplitude, period, and the equation of this curve shown below here. Wow. Well, it looks like it's starting at a maximum. So it's starting at 0, 3, a max. And the cosine usually does that, so let's use the cosine curve. Next section, we'll see how we could actually come up with a sine formula for this. Let's get some of the key information here now. The amplitude is going to be the max minus the min divided by 2. So that's 3 minus a negative 3 over 2, and you get 6/2, or 3. Now some of you could have seen that right away, that the midline is at 0, the x-axis itself, and you're going 3 above and 3 below, so there's your amplitude of 3. You didn't have to break out a formula for it. The period we spot from here, and that's one cycle of this function. And it looks like it ranges from here to here. So that's from 0 to 8, so the period equals 8. Well, now for coming up with the equation now, we've got the amplitude, that's a coefficient in front, and you get y equals a times b, a times the cosine of bx, okay, where a is the amplitude, and the period is 2 pi divided by b. So we've got the amplitude ready to go here. We've got our y equals 3 cosine bx. B is a little trickier though. So to get b, we have to say the period equals 2 pi divided by the absolute value of b. So the period is 8, 2 pi, and b is going to be positive in this case. So b equals 2 pi divided by 8. So b equals pi over 4. So we can put that all together into our formula then and say y equals 3 cosine pi over 4 times x for our equation. Okay, example 3. Solve the equation 6 sine 2x equals 5 for 0 to 2 pi and give answers to the nearest hundredth of a radian. Well, there's a couple approaches on this. There's the graphing approach, and then there's the algebraic approach. Let's start with the algebraic approach. You have sine 2x equals 5/6. So we get 2x equals the inverse sine of 5/6. 2x equals the inverse sine of 5/6. And so we get 2x equals, off the calculator, we get 0.99. But if you just stop there, you're not going to get all the answers. Because basically now, if x is ranging from 0 to 2 pi, we have to anticipate that 2x will range from 0 to 4 pi, which is roughly 12. So we have to think of more answers. And basically, you're going to keep on adding on pi n to this. Also, we have to consider the fact that on the unit circle, we get a y-coordinate of 5, 6, and 2 spots, the one that the calculator just gave us, a 0.99, but there's also one up here. And that you're going to get from doing pi minus 0.99. So, or 2x equals pi minus 0.99, which is 2.16. 2x equals 2.16. Now notice if I just divide by these two, I'll get x equals 0.49, rounded to nearest hundredth, or x equals 1.08. But watch what happens when we take the graphical approach. I graph 6 sine 2x, and also y equals 5. And I can see it's clearly crossing 4 spots between 0 and 2 pi. That's because of this shrinking of the period. And so from 0 to 2 pi, we got twice as many answers as we did before. How do we get those other answers algebraically? Well, to get these two answers, you have to consider the fact that 2x equals 0.99 plus 2 pi n. So there's actually an infinite solution set of these, 0.99. Now let's add 2 pi on to that, and you get 7.27. And 2 pi onto that. Well, I think you can see that's going to be way too big for our 0 to roughly 6 range. So when we divide these two out, we get 0.49, and we divide 7.27 by 2, we end up with the 3.63, and that's this other answer right here. That's two of the answers. And you can also say 2x equals 2.16 plus 2 pi n. So x equals 1.08 plus pi times n. So we get 1.08, and we keep on adding pi onto that, 4.22, and then add pi into that, and you get like 3.7 oops, that's out of range. So that's why we only need those 4 answers. Okay, flange out.